Before moving into the topic, let us understand some basic definitions. Let us start with what is blood pressure. So what is blood pressure? That is, it is the pressure exerted by the blood in the walls of the blood vessel. Now, we know the normal value of blood pressure, that is 120/80. The first one, that is the 120, is the systole and the 80 is the diastole. What is mmHg? We know that the blood pressure is being measured using sphygmomanometer, that is, the mercury rises and shows the value of systole and diastole. So, it is being represented as millimeters of the mercury. Our next definition is systolic blood pressure. We know systole means contraction. So, when the ventricle contracts, the pressure exerted by the blood in the artery is known as systolic blood pressure. Diastolic blood pressure. We know diastole means relaxation. So, in the cardiac cycle, when the complete cardiac diastole is happening, the heart is resting. So, the pressure in the arteries felt during the relaxation of heart is diastolic blood pressure. Welcome back to the topic, regulation of blood pressure. So under various physiological conditions, the blood pressure gets altered. So we have four main mechanisms to maintain the blood pressure within its normal limit. Let us go one by one. The nervous mechanism regulates the blood pressure using the vasomotor center. So the vasomotor center is being located in the medulla oblongata and the lower part of the pons. This center has three areas: vasoconstrictor, vasodilator and the sensory area. Let us understand the baroreceptor reflex with the help of this diagram. So, the baroreceptor is located in the heart, where it is located in the carotid sinus and in the arc of the aorta. So, the baroreceptor is located in the heart. So, now it is a pressure sensitive neuron. So, it is a pressure sensitive neuron. So, when the blood pressure is altered, it stimulates the glossopharyngeal or the vagus nerve, which is the 9th and the 10th cranial nerves. So it sends the impulses to the cardiovascular center of the brain. Where does it send? It sends to the nucleus of tractus solitarius. So we saw in the previous slide. The nucleus of tractus solitarius is located in the sensory area. So in the vasomotor center, in the sensory area, this nucleus is present. So it receives the signal from both the cranial nerve, which activates either the vasoconstriction area or the vasodilation area. Henceforth, helps in the regulation of blood pressure. When the blood pressure is increased, so the baroreceptor will send the stimulating impulses through the glossopharyngeal and the vagus nerve to the CV center, that is the nucleus of tractus solitarius. Now what does this do is, it will inhibit the vasoconstriction area and it will excite the vasodilator area. So the parasympathetic activity given in the flow chart means vasodilation. So when the vasodilation occurs, it decreases the cardiac output and the peripheral resistance, leading to lowering of blood pressure. Now what happens when the blood pressure is decreased? When the blood pressure is decreased, the baroreceptor activity is decreased. Now the cardiovascular center, that is the CV center means cardiovascular center, will increase the sympathetic activity. Sympathetic activity means vasoconstriction. So it causes increase in cardiac output and vascular resistance, leading to high blood pressure. Now let us understand what is chemoreceptor reflex. Chemoreceptor reflex is also a sensory receptor which is located very close to the baroreceptor. So now it responds in changes to the chemical composition of the blood. Let us begin with our flow chart. That is, when the homeostasis is disturbed, that is low oxygen level, hypoxia, increased pH, that is increased in hydrogen ion concentration, acidosis, high pH, hypercapnia, excess of carbon dioxide. When the blood composition chemical composition of the blood is altered. The homeostasis is disturbed. Now it stimulates the chemoreceptor. So the chemoreceptor brings the reflex responses in two ways. One, respiratory center, the other is the cardiovascular center. Now the respiratory center is stimulated, which increases the respiration rate, that is RR means respiration rate. Now in the cardiovascular center, it increases the sympathetic stimulation, that is vasoconstriction. Sympathetic stimulation means vasoconstriction, which increases the blood pressure and the cardiac output. So now altogether, when there is an increase in the blood pressure, cardiac output and increase in the respiration rate, the hypoxia becomes normal, that is the oxygen level is normal. The hydrogen ion acidosis will become normal. Now the hypercapnia, that is excessive carbon dioxide, will come to its normal level. So now the homeostasis becomes restored. The kidney plays an important role in the long-term regulation of the blood pressure. That is, when there is an altered pressure, the nervous mechanism gets adapted to the altered pressure, losing its sensitivity. So the nervous mechanism fails, where the renal play a major role in the regulation of the blood pressure. Now, when there is an alteration in the blood pressure, the kidney, so the juxtaglomerular apparatus of the kidney will secrete renin. So, this renin is important for the conversion of angiotensinogen to angiotensin 1. The angiotensin 1 is converted into angiotensin 2 with the help of ACE, that is angiotensin converting enzyme, which is produced by the lung. Now, the angiotensin 2 is converted to 3 with the help of an enzyme called angiotensinases. Then now the angiotensin 2, 3, 4. What does these 3 do? All the 3 together do one single job. What does it do? It causes the constriction of the atriole. It causes the constriction of the atriole, increases the peripheral resistance. So it increases the blood pressure. In addition to it, what does it do? It starts stimulating the adrenal cortex, which is present above the kidney, just above the kidney, which secretes an hormone called aldosterone. So now what does this aldosterone do on the kidneys? So what does it do? It causes the renal tubule to reabsorb the water and sodium. Absorption of water and sodium increases the ECF volume, that is the extracellular fluid volume, which increases the blood volume, leading to normal blood pressure. Now see clearly, see the chart very clearly. The renin will cause vasoconstriction and the aldosterone will cause increase in the ECF. Now coming to the hormonal regulation of blood pressure. Certain hormones like adrenaline, thyroid, aldosterone will increases the blood pressure. Certain hormones like histamine, acetylcholine, bradykinin, prostaglandin will decreases the blood pressure. Now, in addition to the nervous, renal and the hormonal mechanism, some local substances in the body will also regulate the blood pressure. There is a substance in the body called endothelium derived constricting factors, that is EDCF. So now when a group of amino acid is joined, it is called peptide. So this EDCF is a peptide which has 21 amino acid. Now let us come to the flow chart. So when a blood vessel is being stretched, it will produce endothelin. This endothelin will do two activation. One activation is activation of phospholipase. Now this phospholipase will in turn activate prostacyclin and thromboxane A2, leading to vasoconstriction and increase in BP. Coming to local vasodilators, it is of two types. One is metabolic origin, another one is endothelial origin. Metabolic origin includes carbon dioxide, hydrogen ion, lactate. Coming to endothelial origin, the nitric oxide itself is a endothelium derived relaxing factor which causes vasodilation, leading to decreased blood pressure. With these four mechanisms, we have coming to the conclusion of regulation of blood pressure. I have referred from standard books, so you can definitely refer this video in exam point of view.